second lesson of 4 on continuity and the intermediate value theorem. Function is continuous if function values are defined everywhere. We say f of c is defined. C can be any value for x, means no matter what value you have for x, we will have a function value, a y value above that x. And the limits at those values are equal to those function values. I would give you true or false questions kind of based off of this situation last unit. I said, if the limit as x approaches c of f of x is equal to L, does that mean f of c has to equal L? And you said no. Because you know, if we're approaching some value c, let's make this a little nicer. You could be approaching a value from the left and from the right, but the function value might not be there. Function value might be down here. The limit exists, but the function value is different. If a function is continuous, the limit exists, and the function value is where the limit is. This is the formal definition of continuity. If we're ever asked to prove something's continuous at a specific location, you'd have to look at the function value at that location and look at the left and the right-hand limits to make sure all three of these are the same. All three must be analyzed to prove continuity. At C. Okay, and we'll do that a little bit. Now, more simply, a function is continuous if it has no holes, no jumps, or no asymptotes. I'll put CONT for continuous. Or jumps. Sorry for being messy there. Holes, asymptotes, or jumps. Now let's look at what jumps, holes, and vertical asymptotes look like. Hole looks like that. A jump will look something like this. Vertical asymptote will look like this. We consider a hole a removable discontinuity. I don't know if you spell removable E-A-B-L-E or just with an A. Anybody? Is this how you spell removable? Or is it, because these two are non-removable, is it R-E-M-O-V and then just an A? I don't know. Look it up. Thank you, Mr. Rocca. Ask Siri. How do you spell removable? Yep.
The answer is removable.
There you go. Just an A. Yeah, just an A. Thanks, Siri. All right. So this is removable. These are non-removable. Why is it removable? Well, you can take just a point and you can place it. And all of a sudden, the function that was not continuous becomes continuous. Whereas here, I cannot place a point anywhere, and a function will still be jumping, and it will still have an asymptote. Okay? Now, when is a function not continuous? If it's ever undefined. And a function is undefined whenever we have a denominator equal to 0. At those locations, we will have asymptotes. We might have holes. We might even have a jump. Okay, and this is just for one single function. Now, how will we know if we have a removable, a hole, or a non-removable? Well, we kind of talked about having removable discontinuities in the first unit. We tried to plug in values into functions. We got 0 over 0. We simplified the function, which removed our problem, and then we could plug in to the simpler function and find a value. Well, that tells us if we can algebraically simplify a function and it kind of removes that problem, that'll be the location of a hole or a removable discontinuity. So I'll kind of say that if you can algebraically remove your problem, those will be removed. All right, first two examples. Evaluate the continuity of the function. If you're asked to evaluate the continuity of the function, really, you just need to find the x values at which f is not continuous. And then we need to state the discontinuity, whether we have a removable or a non-removable discontinuity. Whenever we want to figure out when a function is not continuous, we just set the denominator equal to 0. We figure out what x values will make this denominator undefined, or make the denominator 0, make the entire thing undefined. So we know this is a discontinuity. But is it removable or non-removable? Definitely removable. Why? Because I can simplify this numerator. I can factor it to be x plus 1, x minus 1. And I see I can remove those x minus 1s. I remove that problem, which was preventing me from plugging in 1, making this not just a discontinuity, but a removable discontinuity. Now, of course, we can have functions with removable and non-removable discontinuities. We can have functions with not just one discontinuity, but many, many, many discontinuities. So try this one on your own. First step, of course, is to set your denominator equal to 0. I would advise you factor out an x from that denominator. All right, check with the neighbor. Figure out if they're removable or non-removable. Check to see if they were removable or non-removable. Yep, I can have a function with a hole and an asymptote. Yep, and when we are algebraically simplifying these things, we are removing holes.
So would you consider it only removable? I mean, only non-removable or removable and non-removable? Would you define each individual one?
Both of them are still discontinuities.
So you label both of them as such?
Yes, you label both of them as one or the other. Okay, so 0 and -1 will make the denominator 0. However, I can cancel that x that is factored out, which means 0 is a discontinuity and it's removable. -1 is a discontinuity, it's non-removable. You can have both in the same equation. Remember, removables are all holes. Non-removables typically in these equations are going to be asymptotes. You can have an equation with a hole and an asymptote. You have multiple holes and multiple asymptotes. We can have crazy things going on here. Okay, so you will have to set a lot of denominators equal to 0, and you'll have to like factor and do some algebra to figure out the solutions and stuff like that on your homework. It's good practice for solving equations. N equal to 0. All right, skip that one. Let's do the one on the bottom right. Where do we have a discontinuity, and what type is it? All right, what do we think? Is this x equals 3 removable or non-removable? What do you think, Mr. Beard? Why do you say that? Because I can cancel x minus 3 and x minus 3 right here, right? It would be 1. 1 is the key thing. Do you know what this function looks like, Mr. Beard? A V? No. Most absolute value graphs do look like V's, but not this one. We studied this one a little bit. This bench, you remember? Dispersion A, Mr. Bowman, Mr. Master, Ms. Gross, Mr. Brun.
All right. On the left, it's non-removable because on the left side of the graph, or less than 0, it'll be...
Not less than 0.
Or negative, sorry.
Not negative. Less than 3. It's
Oh, less than 3, right.
Yep.
Less than 3. It'll be -1, equal to -1, because the bottom will be negative, but the top will always be positive.
Yep.
And it'll be positive on the... It'll be +1 on the right, because your top and bottom are both.
Exactly. You think about values like 5. You get 5 minus 3 over 5 minus 3, so you get 2 over 2. If I plug in 6, I get 3 over 3. Plug in 7, I get 4 over 4. If I talk about values to the left of 3, I plug in 2, I get 1 over -1. Plug in 1, I get 2 over -2. Plug in 0, I get 3 over -3. This is a function that we need to be familiar with. This kind of absolute of something divided by the same thing. So even though you kind of can cancel this, you can cancel this only for the positive side, which tells you you're at 1, and you can cancel it for the negative side because absolute value of something is really like when x is bigger than 3, we're going to be talking about this in general. When x is less than 3, we're going to be talking about the opposite of whatever this is. So it becomes tricky, and this is non-removable, and we have a jump. Now this is the only type of function that I know of where you're going to see jumps when given just one equation. All of these other non-removables, these are all locations of asymptotes, vertical asymptotes. And if there was another one, it would be asymptotes. Okay, so typically when we have a non-removable, we will have a vertical asymptote. Typically vertical asymptote. Except for this guy where we have a jump. Now where else, what other types of functions, not necessarily like one equation, but functions, do we have jumps? Piecewise functions have jumps. So let's look at continuities of piecewise functions. Okay, so this guy. We are defined for this function when x is less than 1 with this piece x squared. We are defined for this function when x is greater than 1 for 2 minus x. Okay? I know that x squared is continuous everywhere. I know that 2 minus x is continuous everywhere. The question is, when we leave this x squared function, will we meet at this 2 minus x function at 1? That's all we have to figure out. If we figure that out and they meet at the same place, the function is continuous. If they don't meet at the same place, function will not be continuous at that location. Well, all you have to do then is, if I split this into two pieces, like maybe the top guy and the second guy, I just need to evaluate the top guy when x is 1 and make sure that that's equal to the bottom guy when x is 1. That's 1 squared, plug in 1. That's 2 minus 1. 1 equals 1. We are continuous everywhere. All right, you guys do the second one. Now for this guy, we have three pieces. X squared plus 3 to the left of 1. 10 minus x between 1 and 2. 6x minus x squared to the right of 2. This will be continuous, but do they meet up where we leave the 1 and we pick up the second one? Second guy will be continuous, the third guy will be continuous looking at them individually, but the question is, will they meet up where we leave the second guy and pick up the third guy? You guys work on that. Check with the neighbor, make sure you're good. Okay, not continuous, just at 1. The key is identifying where we leave one and pick up the other. So what the x values are that we're plugging in. First one and the second one meet up at 1. So I'm plugging in 1 into both of those equations and seeing if they're equal. Second and the third one meet up at 2, plug in 2. You could also graph these, but it's essentially the exact same thing as what we're doing right here. So if you want to graph and see visually that you're jumping, and of course, you know, not continuous at x equals 1, that's the location of a jump. If you want to see that jump, graph it. Just maybe not necessarily if you think about the functions that you're dealing with. Okay, let's look at this guy. It looks like 2 pieces, and if we saw this question and this is just x is less than 1/2 and this is x is greater than or equal to 1/2, this would be easy because you just see if this piece meets up with this piece at 1/2. The absolute value complicates things a little bit. Always good to draw a number line when you're talking about absolute values. And we think we're focusing on 1/2. However, if you think about the absolute value making things positive, I could also think that negative 1/2 is also going to be a focus. And here's why. If I'm thinking about big values bigger than 1/2, like 5, well, the bottom piece is when x is bigger than 1/2. So the bottom piece, the 1/2 plus x, is going to be that piece when x is bigger than 1/2. Well, that's also going to be the piece when x is less than negative 1/2. If I talk about negative 5, well, the absolute value of negative 5 is positive 5. That is bigger than 1/2. turns out this is not kind of like a left and a right equation. This being like to the left of 1/2 and this being to the right of 1/2. This turns into an inside-outside type deal, where between the halves we have one function, outside the halves we have another one. And with absolute value domains, you'll always have this inside-outside connection that you have to figure out. Okay? So always with absolute values, think of inside-outside rather than just left and right. So what we thought was just this piece meeting up with this piece at 1/2 turns into these two pieces maybe meeting up at -1/2 and at 1/2. We have to check both locations and see, do they both work or do they both not work, or maybe one works and the other one doesn't. So you guys figure that out. And make sure you know, sine of pi x, that pi x is in parentheses. It's the sine of pi times x, not the sine of pi quantity times x. Check your answers. We're good at +1/2. We are not good at -1/2. So we would say our function is not continuous or discontinuous at x equals -1/2. Okay. We might have problems where we need to make the functions be continuous. We need to find values like a, b, or c values in the following equation so that the function is continuous. So this guy would be like, find c such that f of x is continuous everywhere. This would be find a. Okay, doesn't matter what c is. I know x squared minus that c value is continuous. Same with 4x plus 2c. That's going to be continuous. But we need this piece on the top to meet up with this piece on the bottom, where we switch from being defined with this guy to being defined with this guy. Or I need this top piece and this bottom piece to equal each other at 5. So remember, a function, add a value, you plug in that value for x, not for c. Take 5, plug it in for x. We are trying to find c. Take 5, plug it in for x here. And then we just solve this equation. 25 minus c equals 20 plus 2c. Subtract 20, add a c. 5 is equal to 3c divided by 3. C equals 5. Okay, do this one quickly. Hit 2, unless I made a mistake. Yeah, never mind. I made a mistake. Subtract 4, not add 4. What happens when you rush, Mr. Messner? Okay. We might have an A and a B. Let's turn these into different values. Turn this from -2. See how it changes. 6x minus 8 when x is less than -2. Ax plus 2b when x is between -2 and 1. 8x minus 2 when x is greater than 1. All right. Top and the middle need to meet up at -2. -20 equals -2a plus 2b. I can't really solve this for a and for b. I could solve it for a variable, but it would be in terms of the other variable. So let's pause there. Let's work on the second guy. Middle and the bottom have to meet up at 1. So the second guy at 1 needs to equal my third guy at 1. Well, this produces another equation with a's and b's. Well, we have 2 equations and 2 unknowns. We actually need 2 equations with those 2 unknowns to solve for those unknowns. There are multiple ways to solve this system of equations. We can either solve one of these for a variable and then substitute it in the other. However, when we have a's and b's that are kind of like nicely lined up, it might be easiest to solve this using substitution. To solve using substitution, you kind of line them up one on top of the other. All right, that's step one. Step two is you multiply either equation by some value so that you create opposites. And we want to create opposites so that when we add these equations together, we eliminate a variable. So I look at the bottom and the top and I see I have two b's. Well, I don't like subtracting things, and you can subtract these equations, but instead what I like to do is multiply everything by a -1 to make this positive, this negative. And, you know, if you wanted to work with the a's, you could have multiplied the bottom equation by 2 if you wanted. And then what we do is we add our equations together. We get the 20 plus 6 is 26. I get 2a plus a is 3a. I get 2b plus 2b is 0 b's. A is 26 thirds. Not nice, but whatever, that's the answer. Then if I want to find b, plug it into one of my equations. It could be either one. 26 thirds plus 2b is equal to 6. Let's work with some fractions here. 2b is equal to 6 is 18 thirds. 18 thirds minus 26 thirds is -13 thirds. Divide by 2, you get -13 sixths. Fun. Not a nice answer. Usually these problems work out nicer. And the problems you did in the past with these systems usually are like, A is 3, B is -2. But sometimes they'll be like this. Okay. Moving on. Find B so that this function is continuous. Function value does not exist when x is 4 for this piece in general. We talked about those last couple problems. Each of our pieces were continuous everywhere. Well, this piece is not continuous everywhere. It's not continuous at 4. Well, the key is we need to find where this location is. This turns really into a limit problem. Well, as we're approaching 4 from the left and the right, what value are we approaching? To do this algebraically, we simplify. We cancel. We plug in 4. And we say this limit is 8. Well, for this, with a hole to be filled in with this value b, b's got to be 8. Kind of another way to ask a limit problem. Okay. Intermediate value theorem. Do you have to write down this definition? Maybe. Better for you to understand the concept and then write it down if you really need to. At least you can write down intermediate value theorem. Okay? I'm going to say it. If f is continuous on a closed interval and k is any number between f of a and f of b, there exists at least one number c in a or b, a to b, such that f of c is equal to k. Sounds crazy, doesn't make sense. But here's what this theorem does. If, and this is just an example. This is not like me showing you the theorem. If I say like f of 1 is -3, and I say f of, say, 4 is positive 5, and I say that my function is continuous, well, then I know there will be some value between 1 and 4 that will produce a value, any value, between negative 3 and 5. So I can say there exists a C such that f at this C value equals, I don't know, some value between negative 3 and 5, 0. And why does that make sense? Well, look at the graph, and let's draw a graph here. If I have the point 1, negative 3, and I have the point 4, 5, and I know that my function is continuous between those 2 points, I will always say, no matter what, I know that this function has to cross that x-axis and produce a y value of 0. So it doesn't matter how you connect these 2 points. Since we're continuous, we do connect them, and we can go down here, we can squiggle a little bit, but I know that somewhere here we have a C value such that we have this 0 y value. Now, the way that the definition states it is we have some A value and some B value that are X values. We have 2 different Y values, f of A and f of B. So we have 2 dots. Then we say, okay, K is some number between f of A and f of B. K is some Y value. If this function is continuous and there's no holes or asymptotes or jumps, then I know that somewhere between f of A or f of B, we will hit that K value. That's an intermediate value theorem. So I can connect f of A and f of B however I want to. There's at least one location, one X value that produces this Y value K. Does that make sense? Nod your head yes, shake your head no, or don't move if you're not paying attention. Okay, great. Well, this is what we're going to do with this. You might be asked, explain why this function has a root in the given interval. A root means a 0, or when f of x is equal to 0. So explain why 4x cubed minus 6x squared plus 3x minus 2 has a solution when that thing is set equal to 0 between 1 and 2. First thing I need to make sure of is that the function is continuous. That's important. If the function is not continuous everywhere, or at least in that interval, then this theorem does not apply. The next thing I have to do is show that f of 1 and f of 2 are, 1 has to be higher than 0 and 1 has to be lower than 0. So I just have to find the function values. I plug in 1, I get 4 minus 6 plus 3 minus 2. That's negative 2, that's 1, that's negative 1. I plug in 2. I get 32 minus 24 plus 6 minus 2. That's negative, that's 12. That's 18, that's 16. Since f of 1 is -1 and f of 2 is 16, then there exists some x value between 1 and 2 such that f of x is equal to 0. And you have to include, and the function is continuous. So since f of x is continuous, we have a value less than 0, we have a value greater than 0, we can say that somewhere between this 1, -1, and this 2, 16, I don't care where, I just know somewhere. It might be more than one place, it might be 2 locations, it might be 3, but I know it has to cross at least once. Okay? And we have a root for cosine between 0 and pi. Cosine of 0 is 1. Cosine of pi is -1. There is some location between 0 and pi where cosine is equal to 0. And you know that location anyways. What is it? Pi over 2. Intermediate value theorem, make sure that you know that. And I don't care that it's a pi or 2. I just know there is an x. And it's because this function is continuous. Very quickly, you can look at this problem and just give me the answer. So say this function is continuous. It's continuous between these values, -1, 3, 1 and b, 3, 5, 5, 4. What does b have to be? So the function must have 2 roots. Nope. What does it have to be so that I know that we have 2 roots? What? 0, I would know it'd have 1 root. It has to be negative. B must be negative. Why does B must be negative? Because that's the only way I will know that I will go from here back up to here and cross the x-axis twice. This B must be negative.